Hello world, it's me. I'm back to this STD bus 8085 single board computer project. I've been building it out and so far everything's looking pretty good. I've been mostly verifying the memory mapping since that was the highest risk portion of this design. And I thought I'd take a break from testing the board to make a little primer video on memory swapping, since the ability to dynamically remap memory is a key aspect of this design, and hopefully if you build one of these you'll take advantage of that capability. By remapping memory, we're talking about changing the memory addresses of these onboard memory devices as well as the 8155 and the onboard port while a program is running on the board. So we're going to dynamically change the memory map of this board while a program is running. And in this video, we're going to talk about 4 techniques for memory remapping. 3 of those techniques are pretty generic, and one of them is bonehead simple and quite obvious. But the 4th technique is a unique parlor trick, and it's somewhat unique to this board. So even if you're familiar with memory swapping techniques, it may be worth skipping ahead to that technique before you go. Now, as a refresher, on this board we have 3 memory devices, M1, M2, and M3, and there's 2 memory maps. So we have an onboard port, and if we just change a bit in that onboard port, we can flip between the configurations of the default map and the alternate map. And with those 2 memory maps, each of these 3 memory devices, as well as the 8155 and the onboard port, is designed that they can be selected from an address block anywhere within that 64K memory space. So other than making sure that memory is not overlapped within any one of the 2 maps, there's no restriction on placement. You don't have to have M1, M2, M3 in any particular order. You can put them anywhere you want in memory. So let's say, for example, that you've got 2 devices. You have a RAM and a ROM set up. And when you first start up, you need to have the EEPROM down at 0 to provide a bootloader. But then when you're running, let's say you're running CPM or something, that once you've booted, you may need to have the RAM down at 0. So you need to be able to switch these 3 memory sockets around on the fly and put the RAM where the EEPROM was, move the EEPROM someplace else, and get the system into whatever configuration is necessary for whatever operating system you're running. And the problem with remapping memory on the fly, of course, is that here you are running a program from memory, and as soon as the program executes the instruction that remaps the memory for these devices, the program counter that has a memory address for the next opcode fetch, but if that device has moved, the address that program was going to fetch the next opcode from is now gone. And that next memory address, it may be now in a different device, or it may be nothing but a hole in the memory. That memory may not actually exist anymore. And so that processor, when it fetches from its existing program counter, it may get junk, it may get nothing, but if we plan it right, it will just get the next instruction and it can continue the program. So I've been playing with that memory swap techniques, and I've come up with 4 systems, and I've grouped them into 4 categories that I want to go over in this video. And I think it might be useful for others when they start playing with this board to have some examples of how to manage the memory in this. And to keep them straight, I've given them descriptive names, and the 4 techniques I've come up with are, the first one's called the MCP, the second is the wormhole, the third is the Mr. Magoo, and the 4th is the respawn. And by far the simplest and easiest to grasp is the use of a static master control program, or MCP. Now, when using a master control program, the idea is just very simple, that the memory is remapped and everything else is changing, but the memory block that's executing the MCP is static. So its address remains the same while everything else in the system is changing. So if you have your MCP running in this M2 socket, for example, you can swap M1 and M3 around, or you can just move these anywhere you want as long as you leave M2 alone, so that the program that's running in M2 doesn't have to worry about its memory changing or dropping out from underneath it while it's incrementing its program counter. If that's the case, there's absolutely no drama. The program can swap the memory map around since its own address is not going to change during the swap. And I think the MCP idea is simple enough that I don't need to work through an example on that one, but I will have examples for the other. Okay, the wormhole is along the same idea, and in the wormhole method, it still needs a small portion of memory that is mapped the same in both the default and in the alternate mapping. So in the MCP, the concept was that this entire socket would stay in the same spot. With the wormhole, we only need to have 3 bytes that stay in the same spot. Now, on this board, the way I've been playing with it purely for convenience, I've been mapping the 8155 IO and the onboard port the same, whether it's in this standard memory map or in the alternate memory map. And that's just been for convenience, but so far I haven't found any reason to change their mappings between the two. Now, in addition to the ports and the timer in the 8155, the 8155 has 256 bytes of RAM. And if we look at this little bit of code, right after the reset, I have the program create a wormhole up in that RAM by writing 3 bytes of executable code. The first of these 3 bytes is the machine instruction for the port output instruction. The second is the address of the onboard port that controls the map selection. And the third byte is the machine instruction for the PCHL command, which swaps the program counter and the contents of the HL register pair. So here's this example of the code showing where the memory pointer is set up and a move immediates are used to fill these 3 instruction bytes. Then to use this wormhole, the program first fills the accumulator with the value to send to the onboard port. And so that value is going to, you set the least significant bit to 1 to use the alternate memory map, or you clear the least significant bit to use the default map. The program then puts its re-entry address in the HL pair. And that re-entry point will be the next instruction fetched in the new memory map. So the memory map that you're swapping to, you will put in the re-entry point in the HL pair. And finally, the program jumps to this wormhole portal where it executes those 2 instructions. So first, the out instruction is fetched with its operand byte as the port address. The value that was passed to the accumulator is written to the port, and immediately the memory map is changed to the new configuration. And presumably the memory device that sent us here is now moved somewhere else. So we're abandoned out here in this RAM in the 8155. The processor then fetches and executes the PCHL instruction that's out here in the 8155. So the contents of the HL pair are loaded into the program counter. And since this address is our re-entry address into the new mapping, the program counter simply fetches that instruction and the swap is complete. It's pretty flexible since we can dynamically choose where the wormhole is going to spit us back out. All we have to do is load these 3 registers, jump to this wormhole, and it will spit us back out at whatever we put into the HL pair. Now, as I mentioned earlier, a little bit of a downside to both of these techniques, the MCP and the wormhole, is that it requires some amount of static memory so that there was enough continuity for the program counter to just fetch the next instruction out of memory. The wormhole only requires 3 bytes, but still it must be static so the program counter can simply fetch that instruction from the next memory location. So I got to thinking, is what techniques can we use if there's no fixed memory between the 2 maps? And the next 2 examples do not have any static memory requirements, but they do have some memory mapping requirements. And the first of these 2 examples requires that the 2 memory maps have a shared memory space, meaning they're overlapping in the memory space. And the second technique is the opposite. It requires that the 2 memory maps have non-overlapping memory space. So which one you use of these 2 techniques may in part depend on your memory mapping requirements. So the first of these that requires both maps to have overlapping memory space it's pretty obvious, and I call it the Mr. Magoo technique. Just like Magoo, the program counter is going along, it completes the out instruction to change the map, and just before taking the next step, the new memory device is mapped to the current program counter, and therefore the next fetch results in a valid instruction that can continue the program. So this means that to use the Mr. Magoo technique, we need to make sure that whatever memory device is being swapped in has the program continue from the existing address from the memory device being swapped out. And in the simplest case, you can just take the address out of the program counter following the out and use that address to org the location in the other memory device with an instruction, maybe something like a PCHL. So in this little code snippet, for example, in the current device, we load the accumulator in HL just like if we were using the wormhole. We mark that address. The $ gives us the current program counter value, so we set Magoo to that address. Then in the new memory device, we org a PCHL instruction to continue the code and reset the program counter to wherever the program reentry point is. Or if you wanted to, you could just continue the code from this point. You wouldn't have to do the PCHL. You could just continue the code running from that point. And to avoid having the register preloading in the old device, it may be more convenient, I guess, to just have the 3-byte jump instruction in the new device, just like we did in the wormhole. So it'd be like this. In the current device, you would just load these registers. You would then output to the onboard port, and then you would switch to the alternate map. And then in the new device, you would have this orged at Magoo, and you would just have a jump. So instead of the PCHL, you would just have a jump. And that would jump up to a re-entry point somewhere else. Now the advantage of this is that if you put the address only in the replacement device, then you don't need to know the re-entry point when you're programming the first device. So if you make a change in the replacement device that changes the address, it may save you from having to reprogram the first EEPROM. But the way I've been doing this is I've been running both of these programs together and assembling them together as one file. So they're privy to where the other program is. I don't have to do anything manually. I just have everything automatically mapped back and forth. And what I think is the cleanest way to do the Magoo is to reserve a place at the same memory address in both devices that will occupy the memory location, like in this little code snip. So in both devices, they're going to occupy a little bit of memory space. I have a little routine that loads the register and outputs to the port, and then the next instruction is where to jump when re-entering from the other device. So both devices have this little bit of code in the same place, meaning at the same address. The only thing that's different is where the continued program jumps. And if you have these together in the same file when you run through the assembler, you don't have to manually manage anything. And it's just more convenient. I've picked this little address place way up in the top of the EEPROMs. Now, I don't know how your mind works, and sometimes I don't even know how my mind works, but the backstory of why I picked up this STD project rather than the Intellec 8 project that I was planning on is, as I had mentioned, I had sort of been thinking about how to manage the memory swap when the missus and I were watching a Bette Davis movie. And in that movie, there was a bit part played by Natalie, what's-her-face, who was the millionaire's wife, Lovey, on Gilligan's Island. And before Jim Backus was the millionaire, he was the voice of Mr. Magoo. While thinking about Mr. Magoo, my mind somehow swapped over to thinking about this board and just continuing memory continuity a la Mr. Magoo, which then led to the wormhole technique, and that led to this final technique called the respawn. So while Magoo required overlap in the memory space, the respawn must not have memory overlap, meaning in this case, when Magoo is walking on the building ledge, he actually falls off the ledge because, say, the crane operator was sick that day and didn't swing the girder in place right in time for Magoo to step on. And actually, now that I think about it, this respawn technique could also be included just as a little bit of an insurance policy in case your code gets away from you and it suddenly dumps your program counter into a hole in the memory. So even though you have other techniques of managing your memory swap, this respawn actually might be something that's worthwhile to put in the code anyway. The respawn just as well could have been called the abracadabra method because it'll seem pretty mysterious to the uninitiated. Or the militarium aureum, as in all roads lead to Rome, because if the processor tries to fetch an opcode from any memory location that does not exist, it will always be led back to the starting point. So the militarium aureum for Rome, but hexadecimal address 38 for the 8085. So jump to a non-existent memory location, and the program will continue at address 38. Swap memory maps, and the new map has nothing there but a hole, and the program will continue at hexadecimal address 38. If you try to do the Magoo but the landing memory address doesn't exist, after your Magoo falls off the ledge, he will be respawned at address 38. This is all automatic. You don't need to do anything to make it happen. The only requirement is that there not be anything at that memory address that will put anything onto the data bus. So to see this magic, let's look at what happens if we attempt a read from a non-existent memory location on this board. If the program attempts to access a memory address that's not mapped onto this board, it will presume that address is an off-board read. This off-board logic will change the direction of this bus transceiver U19 from writing data onto the bus to receiving data in from the bus. And if there's not a device out there to drive that data bus, these pull-up resistors in resistor network 1 will pull each of the bits high. So that means that when the processor does that read and nobody else drives the bus, it will fetch all ones, or FF and hex. So in our memory swap situation, when the processor is looking to fetch an opcode after our out instruction that's flipped the memory, and if it pulls from empty space, it will get an FF, which it will interpret as an instruction. So what will the 8085 do when it retrieves machine instruction FF? And you actually have the 8080 to thank for this, and more specifically an 8080 with an 8228 bus controller. Because before everything was combined in the 8085, if the 8080 received an interrupt request, it was the job of the 8228 to create the interrupt acknowledge signal for the interrupting device. But the 8228 had a special feature that if you tied the interrupt acknowledge output of the 8228 up to 12 volts through a 1K resistor, then when an interrupt request came into the 8080, the 8228 would jam an FF onto the data bus as the next opcode. And the 8085 would fetch that opcode and execute it. So if we look up the machine instruction FF, we see that that is just a reset 7 to the 8080 or the 8085. So when it gets that FF off of the bus because nothing was out there in memory, it will execute a reset 7 instruction, and that causes the processor to push the current program counter onto the stack and vector to the address, which is 7 times 8, or to the address 56 in decimal, which, not surprisingly, is 38 in hex. So that's the respawn technique. No matter where your program dies, it will respawn at address 38. But there is a bit of warning with this, and it's obviously not foolproof. A very important point is that you should not attempt to respawn if you go to a memory location that is mapped on board but happens to be empty. So if you mapped 16K but you only had an 8K device installed, that is technically empty memory, but it's mapped on board. And if you attempt to do the respawn technique with that, the offboard logic will not flip the bus transceiver, so you won't get the FF waiting on the bus. You will get whatever is on the onboard data bus during that read. And the onboard data bus does not have any pull-up resistors, so you'll be pulling data from a floating bus. And if you've ever done diagnostics on this, you've noticed that anytime you pull from a floating bus, you're most likely to get the value of the last thing that was driven onto the bus. And in this case, that value is going to be the low byte of the memory address, since the low address byte is what was just on the address data bus before the processor tri-stated it when it switched from an output to an input. So in that case, rather than getting the opcode FF, if the next instruction memory address happened to have the low byte as 56, then you would get the opcode 56, because the floating bus will give you whatever was there last. Let me know what you think of these techniques for memory swapping. Maybe you've got some better ideas to share. Maybe this is all child's play to you. Either way, let me know if you find anything useful. Well, that's it for this video. If I stick with it, I think I'll have this board fully tested in the next week or so, and then if everything checks out okay, I can put the design files up on the website. I did want to mention that somebody placed an order for a bunch of SBC 85 CPU boards, and they've pretty much cleaned out my inventory. So I will be placing an order with the PCB house much sooner than I expected, and the reason I mention that is that it looks like I'm going to be making the next version of this SBC 3870, this F8 board, sooner than I was expecting. So if you have any suggestions for additional features, speak now or forever hold your peace. Okay, then that's it for this video. Thanks for watching. As always, this channel is entirely fueled by likes, subscriptions, word of mouth, recommendations, and engaging comments. I will talk with you later. Thanks for watching. Bye-bye.